Okay, so we're going to talk about interference and the principle of linear superposition, which is a really complicated way of saying what happens when two waves occupy the same space at the same time, which waves can do, but matter cannot. Okay, I cannot have two objects occupy the same space at the same time. It's not physically possible. But because waves are energy, they can completely overlap, pass through each other, okay? Occupy the same space at the same time. And there are situations where we can take advantage of that. And there are situations where it is highly undesirable. Okay? I mean, in this age of electronic devices, okay, and transmission of signals like crazy, okay, we have all experienced some form of electronic interference, okay, and it has been entirely inconvenient. Right? What's happening when that happens for you is not that the signal is gone. It is simply that some other signal that is similar in wavelength and frequency is also in the same place. And so it is messing up the wave that you were trying to receive. And as a result, your device, probably your phone, is not able to understand the waves it's receiving anymore. Okay? What's a really quick solution to try and fix that? Okay, I'm thinking even quicker than turn it off and on. Move your phone. Okay? Take a step to the right or the left. Okay? If there's interference happening, interference is a localized phenomenon. It just means that the waves are interfering there. Okay? There's a very good chance that if you took a step or two to the right or the left, that the interference will be gone. Okay? It just so happened that at that point, it was not working out for you. Okay? Now, that's not always going to work. Okay? Back in the day when Wi-Fi was, well, considerably less good than it is now, okay? It used to be on a similar frequency to your microwave. Okay? You had like the wireless like C, okay, now what are we on, like G or H or something like that. But okay, back then it was on a very similar signal to your microwave. And I remember it was March Madness, and it was like the second round, and I had like 4 games on at the same time. Okay, the Spartans were playing. It was a really important game. It was crunch time. I was watching that. Okay, but you know, I had a couple of other games going on. I was watching them all. I had my laptop, the TV, my phone, and an iPad. Okay, and I'm like watching all of the games at once. Okay, and then my kid comes in, and throws something in the microwave, and the shot is just going up for MSU to win the game. Okay, and he presses start, and all of the devices go down because they're all using the Wi-Fi, okay? And the microwave is now generating waves that are on the same wavelength as the signal coming from my Wi-Fi router. They all go down, and I'm like, no! My kid's hungry, and here I am as a good father going, turn it off, because I'm gonna miss the shot, okay? But it was just a matter of interference was occurring, okay? As soon as the microwave shut off, the Wi-Fi signal came back, okay? Did it actually come back, or was it there all along? It was there all along, okay? There were just other waves getting in the way, all right? So we're going to look at what happens when two waves occupy the same space, okay? Learn the 2 types of interference and understand how that can be applied to practical uses, okay? Most acoustic instruments use interference to naturally amplify the sounds that they produce, okay? It's called resonance. All right. So I'm going to bring up the Slinky again here, but just so you can kind of see this. There's 2 kinds of interference: constructive interference and destructive interference. In constructive interference, the waves are what we call in phase. That means when one is up, the other is also up. Okay? So when they overlap with each other, their amplitudes make the medium go bigger. Okay? The principle of linear superposition says that in order to figure out what the medium is going to do, you add the amplitudes of the 2 waves that are interfering. Okay? So if I've got 2 waves coming towards each other, like in this diagram here on the left, okay, that both have an amplitude of +1, they're coming towards each other, they're going to overlap, and when they overlap, the amplitude of the medium will be +2, law of conservation of energy. Okay? All of that energy is there in the medium, so it has to be reflected. okay, in this shape the median takes when they overlap. Everybody okay with that? It's a pretty easy concept to grasp. Add the amplitudes together, okay? Now, if those two were opposite, then I would get destructive interference. So one of these has an amplitude of +1, the other one has an amplitude of -1, okay? When they overlap, temporarily at least, okay, they will cancel each other out. Now, the key to interference is that it is temporary. It only occurs where the overlap is happening. Those waves will happily go on completely unhindered after they interact or after they interfere. Okay? Interference does not permanently destroy the waves. Okay? It just makes it happen at that one spot. Everybody all right with that? So you can see in both of those, sorry, you can't see because I haven't pulled it down far enough. Okay? You can see that in both of these diagrams now, that those waves, after they interfere, keep right on going with exactly the same shape they had before. Remember, waves are energy. They can pass through each other. Okay? If I put, two cars going towards each other like that, that's not how that's going to end. They can't occupy the same space at the same time. They can't pass through each other. Okay? Waves can. All right, everybody okay with that idea? All right. Now, I'm going to show you the we'll show you the slinky first, and then I'll show you the slow-mo that we took of the slinky. All right, so principle of linear superposition, like I say, is a pretty easy thing to get. Now, here's how I'm going to test this on your unit exam. Okay, I'm going to have a question where I've got two waves drawn on a sheet of, like on a little piece of like graph paper. Okay, so you can actually read their amplitudes off of the graph paper with the lines. Okay, and I'm going to say these two waves are occupying the same space at the same time. Draw the resulting shape of the medium and tell me whether the interference is constructive or destructive. Okay, so if I did that, okay, so let's say I had this wave and that wave. Okay, are those waves in phase? They are. When one is up, the other is up. When one is down, the other is down. They are in phase, 100%. What kind of interference is this going to be? Constructive. Okay, what's the shape of the median going to look like?
A straight line.
It's constructive interference, right?
Oh, I thought, how is it constructive if one's going up, one's going down?
Well, when this one is up, that one is up. When this one is down, this one is down. They're in phase with each other.
Okay,
right?
well, then it'll be bigger.
It'll be bigger, right? The resulting waveform will be the sum of the two waves. So this side will look like this, and this side will look like that. Okay? Now, I could also give you one where it was destructive. Okay? Instead, I say, okay, now it's destructive. What's the resulting waveform going to look like?
Straight line.
Is it though?
It's going to be smaller.
It's going to be smaller. It's going to be like the black one, but smaller, because they're not exact opposites. They're out of phase, for sure, but the principle of linear superposition says you add the amplitudes. So if this one has an amplitude of +2, and this one has an amplitude of -1, then my resulting waveform is going to look like this. Okay? It's going to be smaller, but it's going to look like the first one because it was bigger. Okay? Now, if they were completely opposite, if the red line was just as big but completely opposite the black line, then yes, then the whole thing would be flat. Okay? Everyone kind of understand what I'm looking for there? That's a 3-mark question on your unit exam. Super easy question. Okay? You just have to draw the waveform for 2 marks and tell me whether it's constructive or destructive for 1 mark. Okay, so in the diagram on the left, what kind of interference is this? This is constructive because they're both in phase, they're both up, their amplitudes add up and the wave gets taller, and then they travel on completely unaffected after that, okay? And then I've got these two waves that are completely opposite, traveling towards each other, okay? And then moving away afterwards when they have interfered and canceled each other out, okay? Also pretty common for me to ask, draw waves before, during, and after complete constructive interference or complete destructive interference. Okay? That would be these two situations here. Okay? All right, so we've already talked about that, principal linear superposition. Okay, is it possible for us to get waves that are like several waves and still have this happen? Absolutely. Okay, are these waves here, A and B, in phase? They are. When one is up, the other is up. When one is down, the other is down. They are completely in phase. So this is going to be complete constructive interference, okay? And we're going to get increased amplitude as our resulting waveform, okay? In this situation, these ones are, this is going to be destructive interference because they are out of phase, completely out of phase. When one is down, the other is up. But they don't have the same amplitude, or they don't have opposite amplitudes, so it's not completely going to cancel, but it's certainly going to be diminished.
You said completely out of phase, so is there a thing where it's like partially out of phase?
Yep, and then it's a jumbled mess. And that's usually what we get when we get interference. We rarely have situations, especially with electronic interference, that are completely destructive. Okay? And in fact, this is what a lot of modern warfare uses, okay? In terms of like electronic jamming. Okay? Electronic jamming is basically flood the area with a whole bunch of different frequencies and wavelength of radio waves, so that things can't track properly or lose contact with their source and stuff like that. Okay?
So does the frequency like affect the wave? So if you had like a big frequency and then a smaller frequency wave with like two waves and like the bigger wave, would that?
It would still be a matter of like at each instant you would have to draw, so like I say, it'll become a jumbled mess. But yes, because all of those waves would be in the same medium, they would all be traveling at the same speed. So the ones with the larger frequency would have shorter wavelengths, right? And the ones with shorter frequencies would have longer wavelengths. So they're going to overlap, okay? And it would look kind of like this. Okay, so if I've got that same situation we were talking about before, okay, and I've got a wave that looks like that, that's a fairly long wavelength, a fairly low frequency, okay? But if I had another wave, okay, that had a different frequency, it might go like this. Well, those waves are occupying the same space at the same time, but they're not the same wavelength, so it's gonna be messy, right? And so I would have to go, here, there's nothing, but here, there would be constructive. So the resulting wave would be like, and so it's gonna be like, all over the place. It's going to be a jumbled mess, which is something your phone, receiver, whatever, cannot understand, cannot interpret. It just goes, no signal. There is a signal. It just doesn't understand what it's trying to say. Yeah.
So when you were watching March Madness and microwave interfered with like you watching, would your amplitude been increased or decreased?
Both.
Oh, so
it would have been like this. It would have been a jumbled mess.
So what happens if the wavelengths are the same?
The wavelengths are the same. You'll get either a much stronger signal or a much weaker signal if they're out of phase. Okay. Depends whether they're in phase or out of phase. Okay. Okay. So we can hear interference when it happens with sound. Okay. And this is actually something that's used to increase the quality of sound in both home theater systems as well as movie theater sound systems. Okay? We want to position seats, okay, and thus also speakers, okay, so that every position in the movie theater has really good sound. Right? And so what we want to do is know kind of what wavelengths are going to be present for most things, and we want to have speakers that are emitting those wavelengths positioned at certain spots. That's why there's different kinds of speakers. That's why you got subwoofers. That's why you got mid-range speakers. That's why you've got the little tweeters for the high frequency stuff, and why you put them in different positions, okay, so that they're always producing sounds that are going to interfere constructively where the people or the observers, we call them, okay, are going to be located. Okay, now, if we have this situation here, so I have a receiver and it's emitting a single tone. So it's not music, it's just one tone, all right? So well, you guys don't even know what a dial tone is. You guys don't even get a dial tone on your cell phones anymore. So it would just be like if I hit a tuning fork and I just held it there, it makes the same sound the whole time. So one single tone, okay? But it's got two speakers, right? If I have that situation and I walk around the room, will I hear different volumes of sound? I will. And it's not because I get further from or closer to the speakers. There are going to be spots in that room where the waves overlap and interfere constructively, and there are going to be spots in that room where they overlap and they interfere destructively. Okay? And I'll be able to find them just by moving around the room. Okay? Now, it doesn't work as well in a room like this, because what do the waves do when they hit the walls? They bounce off. And so the reflections are also coming back, okay? And that kind of interferes with the ability to do that. But if you do it in a room that's acoustically well designed, so it's got absorbing materials on the walls to eliminate echoes and reflections, or it's a perfectly anechoic chamber. Okay, I don't know if anyone's ever seen what that looks like. I don't want to ever go in one because I feel like it looks like the inside of a meat grinder. Okay, it's got all these like jagged edges and stuff like that that keep the reflections going different directions all the time. If you had that kind of a situation with this receiver in there, you would literally be able to go like this and hear a really loud sound, and then take another step and hear quiet and hear nothing. Like literally silence in that spot. And then as you moved, you'd be able to hear the volume increase to that area of constructive interference. Take a step to the right, and it'll go away again. Okay? There would be these points of constructive and destructive interference all around the room, because this is what would be happening if I was able to see the sound waves and look down on them from above. This would be an area where I would hear a loud sound. Yeah. Okay. Whereas this would be an area where I would hear
a little bit.
Actually nothing. They're not drawing the crests on, or the troughs on here. They're only showing the crests. Okay? So each line is a crest. That means that there's actually, right, troughs in between each of the crests. Okay, so these would be the troughs for speaker A, and then these would be the troughs for speaker B. Okay? And you can see that I just had an intersection of a trough and a crest right where I drew that dot. Okay? So that would be an area of destructive interference. That would be completely silent. Okay? All the other spaces would be a little bit. You'd hear some sound, okay, whatever, but it'd be a bit diminished. Okay? All right, so there'd be places in here where I would hear constructive interference and destructive interference. Whether you hear a loud sound or a quiet sound is based on a few things. Okay? It's based on the speed of the waves. It's based on the wavelength of the waves. And it's based on the frequency of the waves. What are all those part of? We learned about it yesterday. It's pretty important, so. The universal wave equation, okay? Universal means it's used for everything. It's super important, okay? So, the speed of the waves, the frequency of the waves, and the wavelength of the waves all affect where these spots are going to occur. Okay, so for right now, this person is standing an equal distance from each speaker. Okay, so the waves coming from this speaker on the right, okay, the dotted lines are troughs, the solid lines are crests. Okay, so he's got a crest here. He's also got a crest from the other one. Okay, they're meeting in phase, crest to crest, trough to trough, and they're going to interfere constructively, and he's going to hear a loud sound. Okay, now let's say that the wavelength of these sound waves happens to be 1 meter, because that's what they're showing here, that this is 3 meters and there's 3 wavelengths here. Okay, so let's say the wavelength of these sounds is 1 meter. If I back this speaker up a half a meter, what's going to happen?
It's going to be deconstructed. It's going to trough's going to be the crest.
Exactly. If I move this thing back a half a meter, the waves that come from it have to travel an extra half a wavelength before they get to the person's head. Okay? If they have to travel an extra half a wavelength, they're not going to meet crest to crest anymore. They're going to meet
Crest and trough.
crest to trough. Apparently titrations are very exciting. I don't know, it's chemistry. Waves are way more exciting. Okay, so if they have to go an extra half a meter, this is the situation I would have. Okay, so now I back it up half a meter, and now it travels an extra half a wavelength and arrives out of phase, because a trough and a crest are always half a wavelength apart. Okay? So what determines whether you hear a loud sound or a quiet sound in any given location is how many wavelengths did the sound travel from one source versus the other. Okay? If the difference is a full number of wavelengths, so if I back that other speaker up a full extra meter, so it was 4 meters and 3 meters, what would I hear?
It would be loud again.
It'd be loud again. Even though it had to travel an extra full wavelength, it's still a full wavelength, and so they're going to meet crest to crest and trough to trough. Okay? But if I back it up a half a wavelength, then I don't hear anything, because now they're arriving completely out of phase.
You won't hear anything?
If this was in an anechoic chamber, yeah,
Oh, okay.
I would hear nothing at all.
That's weird.
Yeah. Okay? All right. So, does that sort of make sense to everybody? Okay, so here's the way I would test something like that. Sorry, this is what I was just talking about here. So if I've got these two speakers, okay, and let's say I'm trying to plan, where should I put like a couch in this room so that everybody hears a really good sound, right? Well, I would want to put it probably right here, because I've got constructive, constructive, constructive at those 3 spots. Okay, versus back here where I've got destructive, destructive. That would not be a good place to have people seated. And back here I got another constructive spot. So if I'm looking at those spots, okay, this is constructive, even though from this speaker the waves have traveled 2 wavelengths, but from this speaker they've traveled 3 wavelengths. The difference is still 1 full wavelength. Okay, as long as the difference is at least 1 full wavelength, or 5 full wavelengths, or 100 full wavelengths, you will hear a loud sound. Okay, as long as the distance is a whole number of wavelengths, you'll get constructive interference. Okay, but in this situation here, the waves from this speaker have traveled 3 wavelengths, but the ones from this speaker have traveled 2.5. 3 minus 2.5, half a wavelength, I hear nothing. Okay, so if it's a half, 1.5, 10.5, 50.5, as long as it's a half, it's destructive interference. Okay? All right, so let's have a look at how I would ask this question. So can I get you guys to copy that down and the diagram? Okay, this is exactly how I'm going to ask this on your unit exam. I'll give you a minute to get a copy down. Okay, so we were just saying that what determines whether a person hears a loud or a quiet sound is the number of wavelengths the sound has to travel, or the difference in the number of wavelengths the sound has to travel from each speaker to that observer. Okay, so if I have this situation here, where I have an observer who is 2.4 meters in front of one speaker, and the speakers are 3.2 meters apart. Okay, they tell me also, okay, that the frequency of the sound is 214 hertz. Okay, and they tell me the speed of the sound is 343 meters per second. Okay, so what determines whether he hears a loud sound or a quiet sound is the number of wavelengths traveled, or the difference in the number of wavelengths traveled from each speaker. So what 2 things do I need to know before I can determine whether he hears a loud or a quiet sound?
You need to know how far it is from that speaker to the right.
Yep, I need to know how far he is from the other speaker. How do I get that?
Pythagorean.
Just use Pythagorean theorem. Okay, so we'll just say that we're looking for this side here, so that's going to be the square root of 3.2 squared plus 2.4 squared. I'm pretty sure it comes out to 4. Okay, we'll double check here. So 3.2 squared plus 2.4 squared. Okay, 4.
Well, he'll probably hear no sound because.
Well, we'll find out. Okay, we don't want to guess. Now, that said, in a question on a test, it says, "Does the person hear a loud or a quiet sound?" And this is a 6-mark question. Are you getting 6 marks if you flip a coin and guess loud and you don't show any work for it? No. Okay, this is like one of those questions where no, I'm not giving you all 6 marks because you guessed and had a 50-50 chance of guessing. That doesn't make you a brilliant guesser. Okay, so you actually have to show the work on this one. I give you a mark if you guessed loud or quiet, but okay. So I've got the length. What else do I need?
The speed of the waves.
Got speed of the waves.
Lambda.
Wavelength, yeah. If I'm trying to find out how many waves there are between each speaker and the observer, I need to know how long the waves are. Okay, so I need the wavelength. Well, pretty sure I can get that using the universal wave equation. This is why there's not a lot of questions just about the universal wave equation on your unit exam. It's because it's universal and you're going to use it in basically every other question, okay, as well. All right, so I'm trying to solve for lambda. So that's going to mean V divided by F equals lambda. So in this case, that's going to be 343 meters per second divided by 214 hertz. Pretty sure that's 1.6. 1.602, okay. All right, I'll leave all those decimals in my calculator. So now I know the wavelength. So whether the person hears a loud sound or a quiet sound is determined by the number of wavelengths from each speaker. How do I figure that out? If I know the length of one wave, and I know how far those waves have to travel, and I figure out how many waves would be between the speaker and the person, how do I do it?
Length divided by the wavelength.
Right, length divided by the wavelength. Okay, that'll give me the number of waves. All right, so for this one here, okay, 4 divided by 1.6. Okay, 2.4956. Is that close enough to 2.5? Okay, so this is 2.5 wavelengths here. All right, got to do the same thing on the other side. 2.4 divided by the wavelength. Okay, 1.497, close enough to 1.5? Okay, does this person hear a loud sound or a quiet sound? 2.5 wavelengths from one, 1.5 wavelengths from the other. What's the difference in the two? What's 2.5 minus 1.5? 1. Loud or quiet? Loud. It's a full wavelength difference. It's the difference that determines whether they hear loud or quiet, and the difference is a full wavelength. Okay? Lots of times that'll trick people, because they'll see the 0.5s and they're like, oh, 0.5 means that it's destructive. No, if the difference is 0.5, it's destructive. Okay? All right, so that would be, okay, you'd get a mark for your givens, you'd get a mark for your universal wave equation, you'd get a mark for your Pythagorean theorem. Okay, that's 3, 4, 5, okay? And then, yeah, your subtraction and whether you got loud or quiet. Okay, for your 6th mark. So probably a 6-mark question. All right, questions on that one? That is exactly how I would ask it on a test. Okay. Everybody got it written down? Did you, like, circle it? Say, Mr. Coderre is definitely asking one of these. It's the last question in the written response. It's also on the final. Okay, that's all there is for interference. That's all we do. Okay, we do the drawing and we do the speaker question. Okay, now interference is going to come in again when we talk about standing waves and air columns and things like that, because that's basically their standing interference patterns. But hey, as long as you know the destructive and the constructive interference, okay, and you know how to do the speaker questions, you'll be set. All right, I'm gonna give you about a 5-minute break here, and then we are gonna talk about wave behavior at a boundary and see if we can gain a half a day here. Okay, so we've learned about a certain type of wave behavior, and that's interference, okay? Destructive and constructive interference. And now we're gonna look at what happens when a wave encounters a boundary, okay? That means it's gonna go from one medium to another. Now, what properties of a wave does the medium affect? Okay, what property of a medium can never change? Frequency. Okay, so if frequency can't change, the other two have to. Speed and wavelength. Yeah. Okay. Speed and wavelength and amplitude can be affected by crossing from one medium to another, okay, which is a boundary. Now, sometimes a boundary is a barrier. So it's just a wall, okay? The wave doesn't really go into it, it just reflects off of it. Okay? So the wave behaviors you're going to be looking at here are things called reflection, which is when a wave just bounces off. Refraction, which is when a wave comes in obliquely, so not head on. Okay? And as a result, it changes direction a little bit. And diffraction, okay, is another one. Right? We'll be looking at those. So reflection, refraction, diffraction, and we'll be looking at all of those. Okay, so what happens when a wave encounters a boundary? Its wavelength can change, its speed can change, but its frequency will remain the same. Its amplitude will likely change as well. Okay, so that's the second point there. And what happens when the properties of a wave change? Well, sometimes it can change direction too. Okay, so when waves travel, or waves can travel through many materials, okay, but they do so at different speeds. If light, for example, goes from air to water, it slows considerably, right? And as a result, it can bend, okay? If it bends, that's called refraction, okay? Some of it will also reflect. At any boundary, some of both of the things occur, okay? So when a wave hits a boundary between two mediums, some of it is going to get through. Some of it is going to bounce off. What determines how much of each one happens, how much of it gets through and how much of it bounces off, is how alike the two media are. Right? If we're going from, you know, a really heavy bungee cord to a slightly less heavy bungee cord, those are two very similar media, so we're not going to see much reflection. Most of the energy is just going to go through. But if I hook that bungee cord up to a wall, almost all of the energy is going to what? Can the wave energy go into the wall easily from the bungee cord? So most of it will reflect off, okay? Very little of it will be passed through, right? So that's called partial reflection, partial transmission. Okay. All right, everybody with me so far? So in these diagrams here, what we're showing is kind of the nature of that happening, and this is what we call refraction. Okay? In refraction, the waves are coming in at an angle other than 90 degrees. Okay? If they come in at 90 degrees, they just go in, okay, and reflect. But when they come in at an angle like this, the issue is that some of the wave, like this part of it right here, encounters that medium before this part does. So this part, if the medium it's going into is slower, okay, slows down before this one does. So it falls behind the rest of the wave. And what we see is that all the waves get bent. Okay? And because part of the wave slows down and bends the wave changes direction. Okay? It's kind of like if I'm walking along and I've got my arm out, okay, and I hit something, okay, that side of my body is going to slow down, okay, and I'm going to turn, okay, as a result. Okay? The same thing is happening to the waves. They entered a slower medium, okay, part of them slowed down, the other part didn't, so they turn. It's also the same thing that can happen in the wintertime if there's a buildup of snow on the shoulder, okay, and not in the lane you're in, and if you get one tire into that snow, that tire slows down and causes the car to spin out because that side turns, okay, because that side of the car slowed down. Same idea. Are you all right with that?
it would directly in, it would just like change the amplitude.
Right. It would change the amplitude, the wavelength, and the speed, but not the direction. You only see the direction change when the angle is oblique. Okay? Now, it's actually this property, okay, this is what it looks like if we've got like a light beam hitting water, okay? Some of it will get reflected, and some of it will go in, but that stuff that goes in gets refracted and bent a little bit. It's this that jewelers use when they're cutting stones. Okay, so if you're a jeweler and you're cutting, let's say, a diamond, that's reasonably symmetrical. Okay, so if you're cutting a diamond, what you want is for the diamond to sparkle. Okay, that's why we cut diamonds the way we do. Okay, raw diamonds, they just look like a beat up clear rock. Okay, but when you cut them at the right angle, light comes in and only comes out the top. Okay, it can't pass out the bottom of the stone. So what happens is light comes in, hits the diamond, and diamond actually slows light down a lot. It has a very high refractive index. So it bends this light, and the light goes down and hits the bottom facet, any side of a diamond is called a facet. Okay? When it hits that, if this angle is cut correctly, it can't escape. Okay? It's something called the critical angle. And it, instead of going through, it will just reflect. And it'll come over to this side and reflect. And it'll go back out the top. Any light that comes in on the sides or in the top cannot escape out the bottom. So it always comes back out the top and it sparkles. Okay? Now, here's how the jeweler can tell with his little monocle whether a diamond is real or fake. All they have to do, and it literally takes them 10 seconds, is look at that angle. Okay?
But what happens if the people that are cutting it just cut it wrong? Cut the angle wrong?
Then your stone would look like crap. They'd know that too. Okay?
Could they tell it's real? Oh, but like, could they, oh, it's real, but the angle's wrong?
They could say whoever cut this didn't do a good job.
Okay.
But if it's a fake, if it's a cubic zirconia, which is made of glass, that angle is much sharper. I didn't do a very good job of drawing that, but okay? The angle is like way different because its refractive index is considerably different than diamond. Okay? Just for reference, the refractive index of diamond is 2.42, but the refractive index of zircon, which is what cubic zirconia is made of, is 1.90. Okay? They're considerably different. And so a jeweler can tell just by the bottom angle whether it's real or fake. Okay? So, the lesson here is that if they're worth giving the ring to, they're worth giving the real thing to. Okay? Also, they'll find out. Okay? They will, I promise. They'll always find out. I am smarter than that. Okay? My wife, totally worth it. Gave her the real thing. Okay? But I had friends who not so smart. You pay for that one later. Okay? You do. All right, so don't skip it. Okay? Get the real thing. Because it's really, really easy to figure it out if you know what you're looking for. Okay? And now they even have like a little device that just shoots light down into the top facet and then basically just measures like the how much of it gets out the bottom. Okay? So yeah, they can tell it pretty quickly. Now, if I have a diamond in air, it sparkles a lot. What happens if I put it in water? Will it sparkle as much? It actually won't. No, actually it'll sparkle a lot less. Because the cut is only good for the interface between diamond and air. If the interface becomes diamond and water, then the change in the refractive index is different. Okay? The refractive index of air is like 1.00009. Okay? It's basically nothing, right? But for water, it's, 1.42 or something like that. So if I go from 1.42 to 2.42, the refractive change is not as much. Stone doesn't sparkle as much. Okay. All right. It's why, like when they show, like people finding treasure underwater and they show the jewels all sparkling underwater, they don't do that. Okay? Jewels are cut to sparkle in air, not in Okay, so making sense? This whole going from one medium to another is going to cause a change in speed. It's going to cause a change in wavelength, not a change in frequency, and a change in amplitude. Okay, so wave energy that's incident on a boundary between two medium can either be transmitted, reflected, or both. Usually it's both. Okay, in like 99% of situations, both are going to happen. Okay, so we call that partial reflection, and the determining factor as to the amount is how similar the two media are. Okay, if I'm going from one medium to another, like I said, the two bungee cords that are basically the same, I won't see much difference. But if I tie a bungee cord to a wall, I'm going to see a lot of reflection in that situation. Okay, now there are some rules to what the reflection looks like, okay, when you go from one medium to another. Okay. If you have, let me grab another spring here. I have lots of springs. Okay. So, that one's bent. Okay, let's say that I have these two slinkies, and they are attached to each other. Okay, oop, you see there. Of course you wouldn't cooperate right now. Okay, so if I have these two slinkies attached to each other, okay, and I'll get Xavier because now he's got a job experience. Okay. And I'll get you to go almost to the other wall, just because we have so much more of it this time. Okay, are these two media both pretty similar? Yeah, I mean, they're both slinkies, right? There really isn't a whole lot of difference from one slinky to the next. So when I make a wave, that worked well. Why you gotta be like that, slinky? Okay, if I make a wave, and this time hopefully they'll stay together. Okay, was there very much reflection at the boundary? I'll do it again, but I've never had this much trouble with this demo before. Okay, the first time, was there very much reflection? There was a tiny little bit, okay? And it was actually upright, which means that basically it's going from identical medium to the next one. Okay? If I attach this to a different kind of spring, you're not done digging. Okay, was there more reflection? Okay, like it was noticeable that time, right? Okay, and where does it travel faster? The slinky or the heavy spring? And the slinky, right? Okay, way slower in the other spring. Now watch the reflection. Is it to my right or to my left? It's hard to see, it's a small reflection, but it's this way. It's to my left. Okay? When I had the two identical slinkies, it was to my right. But when I have it going to a slower, heavier medium, the reflection is the other way. Okay? This is the rule we're going to learn about tomorrow. Okay? What happens at a boundary and how we can tell whether it's going into a faster medium or a slower medium based on just the reflection. All right? Okay, we'll leave it at that for today. Thank you, Dave.
So if you on this side, it would stay the same, like it'll go slow in the heavier one and then lighter there.
Yeah. So we'll go really slow in that one, then we'll speed up when it hits the center. Hopefully tomorrow we'll have a little bit of time for you guys to experiment with the sprays. Notice I didn't say play. Yep. Yep. They're pretty, yeah, the two big ones? Yeah, they're pretty close. Probably because of the way it attached. Yeah, if I could have made it like so that they would have just gone right together, there would essentially been no boundary. There's just really not a way to make that work.